Hello, we're going to take a look at a problem dealing with blood clotting time. Blood clotting time varies depending on the type and severity of the wound. The clotting time in blood for humans is normally distributed based on a specific scenario. The mean clotting time of blood is 7.45 minutes with a standard deviation of 3.6 minutes. We're asked what percent of individuals will have a clotting time that is less than 2 minutes or greater than 11 minutes. So I have to tell you a little story before we get into this. I attended a presentation on the development of open heart surgery, and as the speaker was talking about the trial process and developing the valves for valve replacement, they had been using large dogs because a large dog has a similar size heart as a human as the test patients. And dogs have a very short clotting time. And so one of the breakthroughs in the research was to switch to using a calf, because a calf, and cows in general, have clotting time much more similar to humans, and so they had greater success. And so I just found that to be such an interesting tidbit of that whole process of developing the open heart surgery and the ultimate success of that procedure. So back to our problem. Keywords that help us to solve this problem is that it is normally distributed. So that to me means that I am going to use a normal curve. So I draw myself a bell-shaped curve and I put in the horizontal axis. I divide that directly in half. I know that in the middle is where the mean is located, and we're told the mean here is 7.45 minutes. I know that the normal curve gets divided up into standard deviations, and we care about the first three on both sides of the mean. So this is the positive 1, 2, and 3 standard deviations. On the opposite side, again dividing into thirds and fixing up my normal curve a little bit there, -1 standard deviation, -2, and -3 standard deviations. So we are asked about two different times. We're asked about 2 minutes and 11 minutes. So I need to calculate the z-score for each of those. So we know that z is to take the piece of data, subtract the mean, and divide by the standard deviation. So finding z for 2 minus 7.45 divided by 3.6 gives me a value of -1.5, and that makes sense to me because we recognize that to be below the mean. So right about here would be the value for 2 minutes, and we know that z for that is 1.5 negative. And so then 11, so z equals 11 minus 7.45 divided by 3.6. And I do the math for that, and I get exactly 1. So that makes it easy. I already had that labeled. So right here is 11 minutes, and it is 1 standard deviation. So z is equal to 1. Labels on these answers are standard deviation. The z-score tells us how many standard deviations away from the mean. Now, the problem, though, is not in terms of standard deviations. The problem is in terms of percent. So it wants me to figure out percent. I also have to know percent for what area. So let's find our percents, and then we'll come back and talk about what area. So I look at my table. My first z-score was -1.5, so that's right here, 6.68%. My other one was 1 exact, and I know that I use positive and negatives interchangeably, so 15.87. So let's take that information back. So this had a percent associated with it of 6.68. And this one had a percent associated with it of 15.87. So up here I'm reading, it says less than 2. Less than 2 would be this area down here below that line I made at 1.5 standard deviations. And when I use my z-score percent chart, the value given is below. So this is 6.68%. And then it says or greater than 11. So greater than 11 is this space up here. All of these are clotting times larger than 11. And because of the symmetry, values below translate to values above, so this is 15.87%. Wow, got a special line there. Sorry about that. All right, so I fixed my crazy line that appeared there, and what we have here is asking us for the total, the percent that is in either of these two categories. So what I'm going to do is take the 2% and add them together. Grab my calculator and do that math. And so I figure out that 22.55% of people will fall in one or the other of these two categories. So we're going to do an extended example with this scenario. And so give me a moment here as I get to that example. There we go. So from what I had before, so just redrawing a little bit of the detail that I had on my other slide. So that's my normal curve. In my normal curve, we knew from the previous slide that the mean here was 7.45, and we had this marked off into thirds. And the same thing down here. That's a 1. Started making a 3 there. And then positive. All right. So this time it says people who have a blood clotting time of longer than 15 minutes are at risk for hemorrhage. So we can see that we're going to be working with 15. So z is going to equal 15 minus our mean from the previous slide of 7.45 divided by our standard deviation, which was also on the previous slide of 3.6. So I do that math and I come up with 2.2. And that makes sense to me because 15 is well above the mean. So putting that on here, it's a little above 2, between the 2 and the 3. So this is where 15 minutes would be. And I know that because z right there is equal to 2.2. And the label on z is always standard deviations. So it says longer than 15 minutes. Right here. So longer than 15 minutes is this section up here above 15. So in order to figure out a percent, I have to look that up on my chart. So I go back. This time I'm looking for 2.2 and I get 1.39%. So I take that to my problem. And this translates to 1.39%. And that is my shaded area right here, 1.39%. So it says a busy emergency room averages 186 people with open wounds a week. How many of these patients would you expect to be at risk for hemorrhage? So I would expect 1.39% of the 186 to be at risk. So I have to do a little bit of work with percents to totally solve this out. There's a couple ways to work with percents. We know that the percent multiplied by the total equals the part. And so using that idea, I can take the percent and I divide it by 100 to give me a decimal of 0.0139. That's my percent as a decimal times the total of 186 will give me the part. And doing that on my calculator, I get 2.58. So I'll round that up to the next whole person. About 3 people would be at risk for hemorrhaging. The other way to do percents is to do them as a proportion. So for that, I would do 1.39 out of 100, because that's percent is always out of 100. And when I set up my second proportion, I know that it's part over total or is over of. And so this is out of 186, so I put that in the denominator, and I want to solve for the numerator. And then I do the cross product and solve that out and get the exact same answer. So X is approximately 3 people that are at risk for hemorrhage. So one of the big questions is, how do I know when I have to figure out this extra step versus when the percent is the answer? And the key to knowing that is to look at the language. So when I look back here at the problem, instead of asking me what percent are at risk for hemorrhage, they actually ask me how many of these patients. So they're asking me for a number, in this case a number of people. When we look at the first problems that we did, and let me go back to those. Right here, they asked me what percent. So they didn't ask me for a number, but they asked me for a percent. And so it is in the wording of the problem that I know whether or not I need to use that percent to find the number of people or the number of objects versus just giving a percent answer.